So this is part D of homework 3 in separations. What we got today is we're going to derive material and energy balance around stripping and rectifying envelopes and algebraically slash geometrically show how the graphical Ponchon-Savarit method can be justified via similar triangles. So to start off with, I have already drawn our graph that we're going to use or as like a reference. We have our rectifying, so this is going to be our rectifying column. What we have is our distillation going through to our condenser, where our distillate comes out and our cycle begins, what we've seen last time. And I have QC for our heat added into our condenser, and we have our vapor and liquid. So to start off with, we're going to recall our base equation of V equals L plus D, and we're going to just exchange, and we're going to add on to this by turning it into the base energy balance we want to use. So we're going to have our V n plus 1 times our H V n plus 1, which equals our L n times H of L n plus our D times H of D. Also, forgot to add, we have to account for our heat added to our condenser. Now on to our material balance. Move this down real quick. We're going to take in account of our Vn plus 1 and Ln plus D. And I forgot to mention before, but essentially what we're looking at is our envelope. And what this basically tells us is this gives us a brief or a simplification of our process that we need to account for. So since we have our V, Ln, and D outside of this envelope for a material balance, that's what we're going to look at. So this is our first equation, but we want to also put this in terms of compositions. So we got to account for that. So for our vapor composition, we're going to multiply by our vapor, and then our Xn times Ln plus Xd times D. And since we have our Vn plus 1 and we want to have matching variables to say the least, we'll simplify it down to Yn plus 1 times Ln plus D, which equals Xn Ln plus Xd times D. If we go ahead and simplify this further, what we'll get is Ln times Yn plus 1 minus Xn, which equals dxd minus Yn plus 1. Okay, so now what we can do is go ahead and move our Ln, our D over to our Ln, get Yn plus 1 minus Xn, which equals Xd minus Yn plus 1. And that concludes for finding our derivation for our material balance. And now we're going to head over to our energy and derive that. So we're going to start with Ln plus D, as we found that Vn plus 1 is Ln plus D, multiplied by our H bar Vn plus 1 plus our QC, which equals H bar Ln times Ln plus H bar D times D. So now what we're going to do is go ahead and do the same thing we did with the material balance. Oh, here we go. So we're going to have our Ln and then our enthalpy of Vn plus 1 minus our enthalpy of Ln. Oh, and then we're going to move QC over. Right here we're going to have our, should be D times enthalpy of D minus HVN plus 1 plus QC. Yeah, there we go. And then, like before, we're just going to go ahead and move our D over. So we're going to have Ln over D over our enthalpies, which equal enthalpy of D minus enthalpy of Vn plus 1 plus QC over D. And that sums up for our derivation of our energy balance. There we go. Okay, so now to prove that our material balances work, what we're going to have is we're going to plot it. So we have our H and we have our compositions. And if we suppose that our graph is like this, where we have two lines, kind of that. That's not perfect, but should do. And we'll use this. If we have this point on our graph, this is our, some other color, delta D, or our delta D is the sum of our enthalpy of D plus our QC over D. QC over D. And now if we want to go ahead and look at this geometrically, we can just go and draw a straight line down. And if we pick a point, suppose right here, we will go ahead and match that over as such, and then pin this back to this intersection right here. Yep. What we also want to do is label our little components that we will use to prove that this works. So if we use that and our enthalpy of D minus V plus 1, we're going to have labeled as A. We're going to have this part labeled as B. And then in our material balance, we're going to have this as our C and this as our D. So if we take our, let's do red. So if we look at A, our delta D to our first curve is going to be represented by A, which is our enthalpy of D minus our enthalpy of V plus 1. And if we look at our other intersection here and draw a straight line down, this represents our B, which is our enthalpy of V plus 1 minus our enthalpy of our Ln. And if we look at our 2 points connected right here, this is our C, which is our composition of D minus our composition of N plus 1, or our liquid composition minus our vapor composition. And then last one we have is D, which is our vapor composition of N plus 1 minus our liquid composition of N, which is represented right here. As you can see, this kind of looks a little bit like our step functions, or our steps, and this just proves that this method does work. And so now what we're going to do is go ahead and derive for our stripping section as we've already done for our rectifying, and now we're going to do for our stripping. Okay, so now we have our stripping column process here with our envelope, and this is like before, where we have our vapor going in, liquid, our bottoms coming out, and then we have our heat. So starting with our energy balance, what we'll see is our V n plus 1 times our enthalpy of V n plus 1 plus our B times enthalpy of B, which equals our heat from our reboiler, plus our Ln times our enthalpy of Ln. That concludes for the base of our energy balance, and then for our material balance, what we'll see is our Ln plus QB, or equals our Vn plus 1 plus our boiling. Okay, also one thing to note, these are going to have a bar over top because it's not exactly the same as the Ln as we use in our rectifying. So just to have a differentiation of that. And then we're going to do the same thing as before. Essentially, we're going to have our Xn, and then our Yn plus 1, Vn plus 1 plus our Yb times B. Yep. Sorry, yep, this is supposed to be XB since there's a liquid going out. And so now what we can do is sorry, this is supposed to be gone. We're gonna substitute our Ln in. So we're gonna have Xn times V bar n plus 1 plus B, which equals our Yn plus 1 times our Vn plus 1 plus Xb times B. Want to go ahead and make this Vn plus 1 times our X of n minus Yn plus 1, which equals our B times X of n minus there we go. And then finally we want to go ahead and do same what we did with distillate, but to our bottoms, and move that over, minus Yn plus 1 which equals x of n minus x of b. And this right here is our first derived equation. And now for our second equation, we're just going to utilize our equation we found here. We have our, keep it consistent, Bn plus 1 times our enthalpy of, oh, I forgot. Also, one thing to note that I changed here, it was our bottoms composition minus composition of the tower. I had it the opposite way, but it's xb minus xn. Just to point out. N plus 1 plus our bottoms times our HB, which equals our work, plus our, and since what we found here is ln equals Vn plus 1 plus b, we're just going to plug that in. So Vn plus 1 plus our b times enthalpy of ln. There we go, and then we're just going to go ahead and move our components over to combine like terms. So if we have our Vn plus 1, Vn plus 1 of our enthalpy minus enthalpy of ln plus we can make this equals QB plus our B enthalpy of B minus enthalpy of ln. I believe that is correct. And then we're just going to get rid of our B on our right side, move it over. Which equals our QB over B plus HB minus HLN. And this right here is our second, oh, it's really bad, second derived equation. And now similarly what we did with the rectifying, we're going to do with our stripping. So we have our plot, and before we start, let's go ahead and label our ABs and CDs and CDs. This entire section is our A. This is B. We have our C, and then we also have our D. Now, just like what we did with our graph, except a little different, we're going to have our delta B, which this is our enthalpy of B minus our QB of B, or over B. And if we take our point, suppose right there, is it gonna, oh, there we go, where it intersects this right here. And if we go ahead and draw a straight line down, we get a sort of similar pattern. Oh, it's bad. There we kind of go. And if we bring it down, oh boy, we get a similar step pattern, just a little bit different, where this is our A, this is our B, or no, sorry, wrong way. This is A, B, C, and D. And this just shows how our what was it called? Ponchon-Savarit method works also for our stripping column as well as our rectifying. Okay, so now onto the coding section of this. We have our library set up, and we're going to be utilizing methanol and isopropanol, so we have that code for taking stuff off that. To start, we're going to define our bubble temperature function, nRTL, with respect to x and p. We're going to return with np dot sum of x times p dot pvap of, sorry, this is tb terms of t, and then we're going to define our fruit. Sorry, this is supposed to be with respect to p, and then now np return with np dot sum of x times p dot nRTL of gamma with respect to x and t minus x times p dot pvap of t divided by p, all of that minus 1, and then we're going to define our t sp dot optimize dot root underscore scalar fruit, make x naught equal t naught, and then our method is secant dot root. Okay, one little change made that that's supposed to be multiplication instead of minus, and then for here we're going to return with t and this line of code right here. Nope, sorry, this is supposed to be gamma, and then, yep, there we go. If I didn't catch that, that would have been an error. That sucks. And then we'll have our pressure, which is 1 to the times 10 to the 5th, because we're in terms of ATM, but we convert it to pascals. And then we're going to do something pretty similar to what we have in previous homework assignments in terms of arrays. So we're going to have our Z1s with our NP line space 0, L1, and 101. And we're going to have our Y1S, which is going to be an array. Our bubble temperatures, which is also going to be in an array. Okay, so next we make a loop for x1 within our values of z1s. to return with, or no, sorry, in terms of y1 t underscore, this equals our bubble t dot nrtl np dot array. Looks like Gemini got that correct. It's going to be our x1 and our 1 minus x1, so the value, I guess value ahead of it, depending on whether, yeah, or behind it, and of our p. If we take our bubble ts dot append of t, and then our y1s's dot append of y1, and we're going to define our bubble t's as np dot array of itself, which is bubble ts, and Gemini got it correct again, where we have our y1s defined as the np dot array of itself. So for next, we're going to go ahead and start interpolating, and we're going to start with x interp, or sp dot interpolate dot p chip interpolator, hope that might be correct, y1s, and we're going to have z1s. And since we're going to do pretty much the same thing for tx and ty, so we'll start with ty for bubble ts, and then tx in terms of z1s and our bubble t's. And we also want to define our enthalpies. So HVS, so what we're going to do is take p dot hv. This is in terms of y1 and 1 minus y1. We also have our tx underscore interp with respect to x1. Well, that is for x1 in z1s. I believe that should work. Okay, the I is supposed to be capital. There we go. Thank you, Gemini. All right, there we go. Okay, so now what we do is we're going to just do pretty much the exact same thing as we did up top. Gemini got that correct, so it's just interpolating Z1S and HVs. And then we're going to do HLS, which is the exact same thing, except tuned for HL. We have our liquid compositions. Yep, that's it. So what we got here now is our parameters. So we've already been given our flow is 1. We're going to have a 45 by 65 mole percent of methanol and isopropanol feed with a 96% distillate recovery of methanol and a 98% mole percent purity and a reflux ratio of 5. So I've already got those put in for the sake of time. Though we do have a bunch of equations that we do have to solve for. So we're going to start with WD, which equals RD times ZF times F D, which equals WD divided by XD. And then we want to find our bottoms equation, which is F minus D. If we go for WB, this is ZF times F minus WD. And then to find the composition of B, do WB divided by B. Okay, so now what we can do is look at our compressor, and we're going to do our rectifying and our stripping sections. So QC, we're going to have R times D plus D, think minus, or I think it might be divided by our HV underscore interp of XD minus HL underscore interp of XD. I'll have to double check if that's a division, and then we're going to have our delta D, which is our Q divided by D, or QC really, divided by D plus our HV underscore interp of XD, and then our enthalpy for feed, which is just HL underscore interp of XD. Okay, so a few things. This is a multiplication. This is supposed to be HL, and this is ZF. And then for QB, for our boiler, have QC plus B times HL underscore interp of XB plus this is D minus F. However, this is multiplied by HL underscore interp of XD, and this is multiplied by HL underscore interp of ZF. And then we're going to have to find our delta B. That's not right, but it'd be Q or HL underscore interp of XB minus QB divided by B. Okay, so now we're just going to go to run it. Oh, I see. Yep. So HL is not defined because we forgot to do that up here. Let's go ahead and copy that here and just change this to LS. Now, yep, there we go. That should work. And now we're pretty much almost set. All we have to do is now define our rectifying and our stripping processes. So we're going to have HV, which is HV dot or underscore interp of Y. Yep, and HL, which is of X. What we're going to return is our delta D minus XD times, I believe, Y minus X plus HV minus HL times XD minus, I think, X. And then we're going to go ahead and just copy this here for our stripping column, where these are all the same. However, we have a slight difference where we do XB, I think so, minus delta B and X minus XB, and I will double check that. Okay, so just a few changes. This is supposed to be XD. Change this to HV, this to HL, and that should be just about the changes. And now we have concluded the more mathematical part of it. So we should make our plot. So rows which equals 1, columns which equal 1, dot add underscore scatter of X which equals Z1S, Y which equals R HV underscore interp of XD, row of 1, column of 1, and we can just go ahead and copy, paste, and change this to HL. I think that should be about it. Then we have fig add underscore scatter of X which equals XD of XD. Okay, and then we have our Y which equals HL interp XD and delta D, and we'll have lines or mode which equals lines, line underscore color which equals blue. There we go. And then we want to do our switch which equals false and set that. Our Y equals XD. So here for I in range of 100, X equals X underscore interp of, I believe, Y. And if X is less than XB, break the loop. Break. Oh my god. There we go. and then fig dot add, okay, almost, this is supposed to be y hv underscore interp of y, and then hl underscore interp of x. Yep, mode equals lines. Our color, however, is RGBA 100, 100, 100, and 0.5, which just translate to how much red, green, blue, and A will we need. And then row equals 1, and column equals 1 as well. Okay, so now if we do if not switch, meaning if it's not false, you can just go ahead and copy this because it's kind of similar. However, instead of xd, we have x interp respect to y, and then we're going to switch around our delta d in front, and then we're just going to add our row, which equals 1, column, which equals 1, and then if we have else, it's basically this. However, if you notice, we took it in account to our distillate. However, this time we're going to take into account for our bottoms. So we'll switch it to delta B, our vapor, and because we're looking at the reboiler now, and that should be all the same. And so now we're almost done. We're going to define our Y rectifying. So optimize dot root underscore scalar lambda y, and it's kind of got it right, but not really. Underscore rec for x and y. X naught equals x dot root, and then we're going to do the same thing for stripping. This is going to be y strip, and the only thing that we really change here is our fruit, and if our y strip is less than y rec, also I did change around the y and x just to note, and switch equals true. Okay, so our y will equal min of y strip y rec. So dot update underscore y axes, we're going to set our range to be delta B to delta D. And let's go ahead and run this. Hopefully no errors. Ah, spoke too soon. Oh, yrec. And there we go. Actually, ooh, that's really big. Fig dot update underscore layout our height. Yeah, let's go with that. Okay, there we go. So yes, this is our graph. What we can see here is this is our delta B, or delta D and delta B, and all our lines start from that point, and you can see the shape of it was kind of how we described it in our notes, or on the written notes. And this is really highly affected by the reflex ratio, which we have currently set to 5. So let's say if we set it to 1, then you can see that kind of a little error, and it only starts from delta D. However, if we make it something like 10, we can see that, or almost kind of see if you pay attention, that the slope kind of increases and it starts to get wider and wider, per se. See if we can go a little bit higher. Yep, you can see that the slope is getting a little bit larger. So this is our Ponchon Savret method diagram, and we've successfully made that.